Hello everyone, welcome to lecture 12. Today the learning objectives are the following. We'll talk about the stress conditions in soil, either in dry soil and saturated soil. And we'll talk about what are the total stress, effective stress, and pore water pressure. And lastly, we'll talk about the horizontal stress. So let's briefly review what are the soil. And soil is made of grain and water and air. So in this class, we talk about these three phases as a representative constituent of the soil. And the condition can be categorized into dry condition and unsaturated condition or partially saturated condition and saturated condition. So in the saturated condition, the voids are 100% filled with water. So you can think of the underwater soil, right? Dry soil, maybe you may think of like desert or very like dry sand, pluviated and sand dune. And we talked about the densities. And there are total density and saturated density and dry density. And also we talk about the water density as a pore filling phase and the solid density, which makes up the grains. And sometimes we use the unit weight instead of the density and stress and pressure. So what is the definition of the unit weight? Unit weight is the weight per unit volume. And so the gamma, we use the gamma to denote the unit weight. And gamma is defined as the density times the gravitational acceleration. So rho g. So if the rho has the unit of kilogram per cubic meter, then this one have meter per sec square, so gravitational acceleration. So then what happens? This is the Newton, right? Which is the unit of the force. So then Newton per cubic meter, right? And if it is like 1,000 Newton per cubic meter, then it's gonna be right 1,000 Newton per cubic meter will be 1 kilonewton per cubic meter, something like this. So then let's think about the unit weight of water. If the rho W is 1,000 kilogram per cubic meter, then gamma W, I'm sorry about this, gamma W will be 1,000 times 9.8 Newton per cubic meter. So then this will become 9.8 kilonewton per cubic meter. So approximately we can say like 10 kilonewton per cubic meter. The stress is the unit, the force applied on the unit area of a certain plane. So if this is the plane, then you apply the force, and this has the area, then stress will be F over A. Right? And also we can also use the pressure term. And the definition is the same, the force divided by the area. But the difference between the pressure and the stress is vector. So it has direction. Right? So in this case, the stress will be in the vertical direction. Pressure is scalar. So it doesn't have the direction. For example, if it's air has its own pressure, right? The P, and the pressure will apply the force in every direction because it is fluid. So that's the difference. Stress is acting on a plane, and pressure acts on every direction. Okay. First up, we're gonna talk about effective stress. And this is the most important concept in soil mechanics. And this indicates the intergranular stress that transmit or transfer through the soil grains. So when you think about the sand pack or some like soil pack in a container, then if you apply the force with some plate, this is the plate, loading plate, then this force F will be transferred and carried by these soil grains, right? Then vertical force, the sum of the vertical force of this all the each. Okay. Let's look at this plane at the bottom plane. The force will be all transfers to this bottom plane. So then the sum of the vertical force that's applied by these each individual grains will be identical to the F. Then the vertical stress, you can compute the vertical stress by dividing the force with the area, F over A. And this will be the effective stress in the dry soil. So let's expand our scope into the field. In a field here, this is the ground surface, and we are looking at the point A, which is at a depth of Z. Here, Z, at a certain depth of interest. We want to know the effective stress that's applied on this point A, or at the depth of Z. So then you can think of this column, soil column, overburden, overlying on this plane A, or here, this plane. Then the vertical effective stress applied on this plane A will be overburden weight divided by the area. So we can think of rho T, that's the total density of this soil, and G, and the Z, and the A. So Z times A will be the volume of the soil of this one, right? And A is the area of this plane, and rho T times G will give you the weight. And divided by the area, then this will be rho T and times G times Z. On the other hand, we can also compute the water pressure at a certain depth. For example, at depth of 10 meters, what will be the water pressure? Pressure will increase with water depth linearly, right? With the depth. So then water pressure here will be rho W and G and Z. Or in this case, the depth will be 10 meters. For layered soil, also you can compute the stress at at a depth of interest. So for example, if this is a Z1, Z2, here in the Z3, and if you want to know the stress at here, then sigma V prime, the vertical effective stress, will be the sum of each layer stress. Right, in this case, the capital N will be equal to 3. Right. Then what will happen when the soil has some fluid? So let's think about the saturated case. So then if you zoom in this case, at the so we are looking at the effective stress at a depth of Z, And if you zoom in, here will be some grain, so this will be like a soil in a container with a lot of grains inside. And there will be a weight, overburden weight, F, which is the same with overburden weight by the soil column here. And in the void space will be filled with water. Right. So then if we measure the pressure of this fluid, so if we measure the water pressure that's filling the void, let's say that that pressure, the water pressure, is U. Then here the force F will be carried by the soil grain, right, through the soil grain, and also carried by this water, and which is expressed as the water pressure U. So partly or the partially overburden weight is carried by water and by particles. So then if you think about this F, the overburden weight, and divided by this area, the A, which is the vertical stress, or you say the total overburden stress, is equal to the effective stress that's supported by the skeleton or the soil grain. And so soil grains makes them skeleton, right? And the pore water pressure, so water pressure. And we can simplify this equation into sigma equals sigma prime plus U. Here, if we write it again here, sigma equals sigma prime plus U. And you can see that the water pressure is U, and there's a stress, overburden stress, and inside you have effective stress, sigma prime. So sigma is total stress on a plane within a soil mass, and U is pore water pressure filling the void, and sigma prime is called the effective stress. Stress is already here. Effective stress acting on a plane. And this stress considers the force transmitted through the soil skeleton only. So please remember this equation. Yep. So then how can we compute the vertical effective stress? So let's think about the point X here, which is at a depth of Z1 plus Z2. And in this ground condition, you have a groundwater table at the location at the depth of Z1 here. And whenever you see this symbol, it shows the location of the groundwater table. This one. And so this is the groundwater table. We'll talk about what is the groundwater table in the next class. And when you see this symbol, this is ground surface. This means, so here is ground surface, and this is groundwater table. So then at a depth here, at point X, the total stress will be, you can get the total stress, total vertical stress using the total density and saturated density, because here beneath the groundwater table it's all saturated. So here the saturation is 100%, but here saturation is less than 100%. Then rho T times G times Z1 will be the weight of this much, and rho set G and Z2 will be the weight, overburden weight by this saturated soil. What about the pore pressure? So the water pressure from here to here will be just the same with the atmospheric pressure. But from here, you can think of the water surface, like sea level. Then below the groundwater table, it's fully saturated so that there's no air. The water pressure will increase with depth. Right? Rho, W, G, and Z. W, depending on the water depth. So here, rho W times G, and the water depth at point X is Z2. So then, if you remember the equation that we just saw before, the total stress is sigma prime plus U, and if you manipulate this one, the sigma prime, the effective stress, will be sigma minus U. So rho T, G, and Z1 plus rho set G and Z2 minus rho W, G, and Z2. And this becomes rho T, G, and Z1 plus rho set minus rho W times G and Z2. And if you know the density here in the layer 1 and density at the layer 2, then you can plug the number here, right? Rho set and rho W and rho T, and the depths Z1 and Z2. Then you can compute the vertical effective stress at the point X. Right. Then stresses in soil again. So we've seen the pore water pressure, right? So if we have a ground surface here, and at the ground surface we have a water table also. So you can think of the case that you have mud, right? The boreal mud. Then you go, there's some water, and also just beneath the water you have the water. You have the ground surface. So it's fully saturated from here, from the surface. Then what will be the effective stress, the vertical effective stress at the depth of Z? Then you have to compute the water pressure, and then you compute the total vertical total stress, the vertical total stress, and from these two you can compute the vertical effective stress, sigma prime. Because it's vertical, you can use the subscript V, sigma V prime. So sigma V prime will be sigma V minus U, and sigma V is here the total stress, the vertical total stress. Then what about the horizontal stress? So there was this one, right? Sigma V and sigma V prime. But we also want to know what are the horizontal stress and effective horizontal stress. Right? That will be the question here remained. So before we go into that, what's the fluid pressure? Let's refresh our memory that we learned from the high school physics. Hydrostatic means that the force acts the same in every direction. So, like I said, if you have a water at a certain depth, maybe like this, then water pressure is acting on every direction, and the magnitude of that is the same, which is UW, and that's rho W times G times Z. So in the soil too, if you have a pore pressure, the water pressure in the pore, U or UW, then that's acting the pressure in every direction. So then the vertical effective stress, likewise, in the same manner with the vertical effective stress, the horizontal effective stress also has the same relation with the horizontal total stress, like this. So this is the horizontal stress in total stress term, and this is the horizontal stress in the effective stress term. So horizontal stress in soil, again, vertical effective stress is sigma v prime, and horizontal effective stress in sigma h prime. In this case, when the soils are at rest, which means that the soil does not move, it's at a static condition under a force equilibrium, then sigma h is this, is k naught times sigma v prime. And here the k naught is called or referred to as the coefficient of lateral earth pressure at rest. And at rest means it's in the force equilibrium. And no movement. So particle doesn't move, and the soil mass is at the force equilibrium, and there's no displacement or deformation, anything. So that's what means the at rest. And typically K naught ranges from 0.3 to 0.6 for sand, and for clay it can range from 0.5 to 2 for clays. So sometimes in the clays the horizontal stress can be bigger than the vertical effective stress. Horizontal effective stress can be bigger than the vertical effective stress. Okay, so then let's develop the correlation with the total stress. So here we've seen that sigma h is sigma h prime plus u, and sigma h prime is, seen that sigma h prime is sigma v prime times k naught, from what we defined in the previous page, right? So then if you plug it in here, then you get this equation. And there's another equation that people use. Oh, sorry, the v here. So that k is sigma a, no, v prime plus u. So here the sigma h is not sigma h prime, it's just sigma h is the total horizontal stress, or horizontal total stress is k times sigma v, which is vertical total stress. Then vertical total stress is sigma v prime plus u. So you can see that this k is not the same with k naught. And here the k is called Earth pressure coefficient. We're gonna have this demo in the class. You can think of the case that you have simple cubic packing, so that the grains are in aligned square in a square manner, and tetrahedral packing, that's more dense packing, but it's kind of triangular pattern. Then when you have a sigma v, that's the force applied on the soil from the top, then what of the sigma h? Which case sigma h will be greater for the same sigma v? So for the same sigma v, which sigma h will be greater? Because of the triangular packing here, this can, right? The force is gonna split into the horizontal portion and the vertical portion, so that the sigma h here, in this case tetrahedral packing, will becomes bigger than the simple cubic packing. here also in the class we'll talk about this example together. Okay, that will be all. Thank you.